Alrighty, so we are now on part 4 of the trig substitution. We've been working through a bunch of examples. We're going to just keep doing these examples and seeing where they take us. So let's just jump right in so I don't waste any time. I want to try and get 2 of these finished. So now we have, now we're up to example 5. So we're going to evaluate the integral dx over square root of x squared minus a squared. Sorry, I already have the dx. We're told a is greater than 0. Okay, so what we're going to do here is we're going to do trig substitution. There's no u substitution to do. And if you look at your chart, you can see what this one is. This is x is equal to a secant theta. And again, I'm going to go ahead and start computing. Dx will be equal to a derivative of secant theta is tangent secant d theta. Okay. And then so eventually I'm going to need it. I'm going to solve for theta, and this is going to be the arcsecant of x over a. So what I'm going to have then, I'm going to just rewrite this integral. I have the integral dx over the square root of x squared minus a squared. If I do my substitution, I'm going to get the integral of, so dx is a tan theta secant theta d theta. Down in the bottom, I'm going to plug in a squared secant squared theta minus a squared. So I've just plugged in what x and dx are. I haven't done anything too crazy yet. Now we're going to simplify, try and get things to cancel. So up top, I still have a tan theta secant theta. Pull the a out of the bottom, the radical on the bottom, and we get square root of a squared, which is a secant squared theta minus 1. We're going to use the identity that secant squared theta minus 1 is equal to tan squared theta. So that's one of that comes from the sine squared plus cosine squared is equal to 1. If you divide everything by cosine squared, you can rearrange it in that. Don't forget my d theta. So just keep simplifying. The a's cancel. I have an a up top, a down bottom. So this is going to be tan theta secant theta. Secant theta, secant squared minus 1 is tan squared. So if I take the square root of that, I'm just going to get tan theta. Again, we're in the first and second quadrant, so we're going to do this so that tan theta is positive. Sorry, we're in the first or fourth quadrant, so tan theta is positive. So if you look at your chart, it'll tell you what the restriction on theta is. So we have 0 is less than or equal to pi theta less than or equal to pi over 2. Sorry, these are just strict inequalities. Or pi is less than theta is less than 3 pi over 2. So sorry, first and third quadrant where tangent is positive, so we don't have to worry about the absolute value sign there. So just let me take a step back and explain what I was doing there. Secant squared minus 1 is tan squared theta. If I do the square root of tan squared theta, this should technically be an absolute value sign because whatever is inside of it should be positive. But because we're in the first and third quadrants, tangent's already always positive, so I'm not going to worry about the absolute value signs there. So all of these are constructed so that I get positive values and don't have to worry about the absolute value signs. So if I simplify this, this is the integral secant theta d theta. And this is one that we can look up. This is the natural log of secant theta plus tan theta plus a constant. And of course, the last thing we have to do is draw this triangle that everybody probably hates at this point. So let's go ahead and do it. So remember, I'm looking at the arcsecant of x over a. So I'm going to let this angle be arcsecant of x over a. So let's see. Secant is 1 over cosine theta. Cosine is adjacent over hypotenuse. So secant theta is hypotenuse over adjacent. So that means if I want to get x over a out of this, I'm going to do that. Hypotenuse is x, the adjacent is a. And by the Pythagorean theorem, I called this y. I know a squared plus y squared is equal to x squared. So y is equal to the square root of x squared minus a squared. So this side is really just square root of x squared minus a squared. Yeah, if you thought, your trigonometry was going away, it's not. These trig substitution integrals come up a lot. I've done them plenty outside of, just these classes. Okay, so let's see. Now, okay, so what we're trying to do is we want to do secant theta and tan theta. So we want to do the secant of the arcsecant of x over a. So I'm doing secant of theta, tan theta up here, trying to figure those out. So secant of the arcsecant, well, these two just undo each other, and this is x over a. So that one was easy. I'm also trying to find the tangent of the arcsecant. X over a. So I take the tangent of this angle. Tangent is opposite over adjacent. So this is going to be square root of, get rid of the highlighter, square root of x squared minus a squared over the adjacent side, which is a. I can plug all of this in now. I'm going to get that oh boy, so the integral, I don't even remember what we were starting with at this point, dx over the square root of x squared minus a squared. This we found to be the natural log of tan theta plus secant theta plus a constant. And when I plug in for, so theta is the arcsecant of x over a. So when I plug in for all that, I'm going to get the ln. Tan of arcsecant of x over a was the square root of x squared minus a squared over a. Plus secant of the arcsecant was x over a plus a constant. So I think I'm going to leave it like that. I'm okay with this form. So that's where I'm going to stop with that one. There's a second way of doing it in the book. You can use hyperbolic trigonometric functions. I'm not going to go over it because I don't think it's not guaranteed that everybody has done hyperbolic functions. So let's see. I'm going to stop the video here because I think that took me a minute to do anyway. I'm going to do I'll do a recap of this one. This will just be a 5-part. So the idea was, this one fit right into our chart. If we have an x squared minus a squared, the substitution I make is x is equal to a secant theta. Figure out what dx and theta are. And then here I'm just plugging everything in. Dx is a secant theta d theta. X is a secant theta, so x squared is a squared secant squared theta. Just going through and simplifying stuff. And so in terms of theta, I find my integral to be this, but I know what theta is. So I have the secant theta plus tan theta. So what I do is I use this theta is equal to arcsecant of x over a. So I treat arcsecant of x over a as an angle. and I say, okay, if I take the secant of this, secant should be hypotenuse over adjacent. So if I take the secant of this, I should get x divided by a, hypotenuse over adjacent. Using the Pythagorean theorem, I can get that side, x squared of x squared minus a squared. And then it's just a matter of determining these, secant of the arc secant of x over a, tangent of the arc secant of x over a, just using the ratios of sides, opposite, adjacent, hypotenuse, whatever they are, in terms of secant and tangent. And then there, plugging it into the integral so that I have it in terms of x and not in terms of theta anymore. So I'm going to stop here. This will be a 5-part lecture. Try and get those last 2 examples done in the next one.